Welcome back, class. So in the last couple videos, we talked about intermolecular forces, right? Those forces that hold molecules to each other. So in this video and the next video, we're going to talk about different phase changes and how these are impacted by the intermolecular forces, right? Because remember, phase changes, right? We're switching between gases, liquids, solids, right? In order to make these changes, we are going to have to break and or weaken some or all of the intermolecular forces that are present. So let's just jump right in here and talk about phase changes. So in general, to change the phase of a material, you have to change the amount of kinetic energy that the particles have, or you have to limit their freedom of motion, right? So if you want to go from, say, a solid to a liquid, right, we have to add energy, right? You have to increase the kinetic energy of that because a liquid is a higher kinetic energy state than a solid, right? The molecules are moving more, right? They have more freedom of motion, right? Solids can only vibrate, liquids can move also translationally, right? They can slide past one another, they can move around one another, right? They can have more motion. If you want to further go to a gas and boil that liquid, right? Again, we have to add more energy to go to a gas, which is even a higher kinetic energy state where the molecules have even more freedom of motion, right? And so we need to add energy to go to a higher kinetic energy state, so to go from a solid to a liquid to a gas, or in other words, to melt and or boil or vaporize, we have to remove kinetic energy to go to a lower freedom of motion state or a lower kinetic energy state. So if we go from a gas down to a liquid, right, we have to cool that down, right? We have to take away some of the kinetic energy. And furthermore, to go from a liquid to a solid, to freeze. Now, temperature is the typical way that we think about this. Now, we should also note that to go between the liquid and the solid phase, the liquid and the gas phase, we can also utilize pressure. Whereas as we reduce pressure, right, we can get a liquid to go to a gas. So for example, if we look at our example of a propane tank here, if we open up that propane tank, right, and propane tank will have liquid, it's a liquid propane tank, right? So it's under higher pressure inside. If I open the valve, those molecules escape to a lower pressure. Notice they escape as a gas, right? So as soon as that material gets exposed to a lower pressure, when you open up the valve, it makes the transition from a liquid to a gas. Vice versa, right? If we increase the pressure, right, we can cause that gas to reliquefy, which is how we get the liquid here in the beginning, right? We take gaseous propane, right, and we pump it in here under pressure, we pressurize it, and apply a little bit of pressure, we get that propane to liquefy, and it goes back into liquid, right? The same effect as cooling it would have. Okay, so we can use primarily temperature, but also pressure can be used to go in and out of these different phases. So we're going to talk more in detail about these phase changes. Now we are going to go into most detail on vaporization and condensation, right? The gas-liquid interchange. And then we'll also talk a bit about, not quite as much detail, but a bit about the solid-liquid interchange and even about the solid-gas phase change. So let's jump right into vaporization. So as I'm sure all of you should know, right, vaporization, right, is the transition between the liquid and the gas phase. Now, typically when we think about a liquid vaporizing, that process is limited to the molecules at the surface of the liquid, right? And some of those surface molecules will have enough kinetic energy to overcome the dispersion forces, or the intermolecular forces that are holding it in the liquid, and they make that transition into the gas phase. They vaporize. Now, what this means, right, is surface area is one of the things that can affect how fast something vaporizes. So the larger the surface area that we have for the liquid, the faster the rate of evaporation will be. So if I have this glass, right, this cup, this beaker here, right, the liquid will evaporate at a certain rate. If I take that same liquid and I put it in, a shallow pan with a lot of surface area, that we're going to have, faster vaporization or evaporation, okay? Because surface area plays a role. Now, of course, only a small fraction of the molecules of a liquid have enough energy, right? But one way that we can increase this fraction or make this fraction even bigger, right, is to increase the temperature, right? So surface area is one way, temperature is another factor that can affect the rate of evaporation. So if we look at the graph here, if we have our liquid at a relatively lower temperature here, you can see that, and look at this graph, right? This is fraction of molecule on the x-axis, on the y-axis, and kinetic energy on the x-axis. So at a lower temperature, only this relatively small area, right, fraction, it has enough energy to evaporate. If I increase the temperature of the liquid, now I have a larger fraction of molecules that now have enough energy to escape. So I can increase the rate of evaporation by increasing the temperature. So surface area, temperature directly can have a rate, can affect how fast a particular substance will evaporate. But, okay, so that's one substance. Now we'll talk about in a little bit about why different substances, right, the intermolecular forces, right, clearly also will play a role if we're comparing different substances and how fast they evaporate. So that's evaporation or vaporization. What about condensation? Well, of course, condensation is simply the opposite of vaporization, right? You have molecules, when they vaporize, some of them will lose energy through colliding with other molecules. They'll collide with the surface. They will collide with the walls. And they recondense back into the liquid when they collide. You may even get droplets of water forming, right, on, say, the surface, right, as molecules collide and recondense. And this is condensation, right? So the transition from the gas back to the liquid when these molecules of vapor lose some of their kinetic energy. Now, if we start to compare or think of these two processes together, right, of course, they're opposites, right? One requires the addition of energy, one requires the loss of energy, right? So they're opposites of each other. If we have an open container, right, so if I just have an open container on the wall, the one thing that you probably notice is that the level of that liquid or the amount of liquid in that will slowly reduce, right? If you set, some water out there, eventually that water will evaporate away. Okay? And that's simply because in an open container, once they vaporize, they typically will spread out or move away from the surface enough that they're not going to recondense. They do that faster than they can recondense back into the liquid. And so the net is a loss of water molecules from that liquid. because the rate of vaporization is greater than the rate of condensation. But if we have a closed container and the vapor isn't allowed to spread out, and so it stays above the liquid, is that you initially will get a lot of vaporization, but at some point the rate of vaporization and condensation will become equal to each other. And the total amount of vapor and liquid at this point won't change. So the idea is that every time a molecule evaporates, one will condense to take its place. And so from the external viewer, right, the amount of gas, the amount of liquid won't change once you reach this point. And this point is what we call dynamic equilibrium. The processes are still occurring, but they're occurring at exactly the same rate, but in opposite directions. And so, again, I lose one molecule of liquid to the vapor, one molecule of vapor condenses back to the liquid. So, just as a sum, right, as an overall picture, nothing changes, right? Even though we have both processes occurring, they don't stop occurring. It just means they don't change. Now, sort of a key distinction as we start talking about equilibrium. Now, if you're going on to take Chem 2, we will get much more into equilibrium in that course, but this is sort of our basic introduction here to our first sort of idea of equilibrium. Now, when we talk in the equilibrium, we have to understand that what's equal is the rates of the two processes. It does not mean that we have equal amounts of the two materials, in this case, the vapor and the liquid, right? We're going to have very different amounts of liquid and vapor in terms of a number of molecules. It's the processes are occurring at equal rates. So here's the same information sort of in a pictorial way, right? So we start out with, only evaporation occurring. We build up some vapor, and now we start getting condensation occurring here. And eventually we get equal and we reach dynamic equilibrium. So at this point forward, right? So once you've reached this point here, right, which is what we have here, notice at this point everything stays the same, right? So the rate of evaporation, the rate of condensation are now equal. And so everything just kind of moves along, right? They stay equal, and so the amount of liquid and the amount of vapor, as long as that container is undisturbed, will stay that way indefinitely, right? As long as you have a truly sealed container and you don't do something to disturb it, right? It's going to stay in that condition. So I alluded to a little bit earlier about what role is intermolecular forces playing here? Well, of course, we know they play a role because in order to evaporate, you have to break intermolecular forces. You have to break those molecules apart to transition them from the liquid to the gas. And so the first point here is if they have weaker attractions, the less energy it's going to take to vaporize. So the easier to evaporate, the less energy, and what that basically means is lower temperature. So vaporization can occur at a lower temperature if we have weaker intermolecular forces. Now, contrastingly, right, it also makes it harder to condense, right? So weaker attraction forces means that more energy needs to be removed before you can recondense them. So, in one sense, it makes it easier to evaporate, but makes it harder to condense. So, that means once you reach dynamic equilibrium here, if you have weaker attractive forces, you will have more vapor, right? Because it's now relatively easier to vaporize and harder to condense. So at that equilibrium point, you're going to end up with more vapor than you would on something that has stronger intermolecular forces. And so that means molecules with weaker intermolecular forces will have what we call a higher vapor pressure. Right? So the vapor pressure is just simply the pressure exerted by the vapor above a liquid. Right? And the weaker the intermolecular forces, the faster the evaporation, the higher the vapor pressure. Also means it's going to have a lower boiling point, but we'll get to that point. Right? So weaker interactions not only lead to a lower boiling point, they lead to a higher vapor pressure above that liquid. Now we have some other terms that we sometimes use to describe these differences. So typically these molecules that have relatively weak intermolecular forces that evaporate quite easily, build up high vapor pressure, are what we call volatile. So things like gasoline, fingernail polish remover, right? We consider these volatile molecules. Liquids that do not evaporate easily, right, tend to have fairly strong intermolecular forces of one type or another. Low vapor pressures are said to be non-volatile. Right? Example, motor oil. And of course, there's a lot of liquids that are somewhere in between, right? That we really wouldn't consider volatile or non-volatile. They're just kind of not at the extremes, like water, for example. Water's not really lumped in with these types of volatile, but it's clearly more volatile than something like motor oil. So, weak intermolecular forces leads to a large amount of vapor pressure or higher amount of vapor pressure, which means it's going to be easier to evaporate and therefore easier to boil. Right? Lower boiling point. So let's talk a little bit more about this concept of vapor pressure. So vapor pressure is just simply the pressure exerted by the vapor above the liquid when you're at dynamic equilibrium. Now, we can talk about vapor pressure at other points, but that's sort of the measurement point, right? It's whatever the pressure is once you reach that state. Weaker attractive forces means more molecules in the vapor, means higher vapor pressure, more volatile liquid. Now, of course, if you have a system in equilibrium, that equilibrium can change, can respond if you disrupt the system. So when conditions change, the system will try to counteract the change, if you will. So let's take, for example, we have a system at dynamic equilibrium here, and we disturb it. So in this case, we're going to increase the volume by raising the piston. Now, what does this do? Well, it raises the volume, so it's going to lower the vapor pressure, right? Initially, right, we get lower vapor pressure because we have the same number of molecules, a bigger volume, less collisions, right? Less pressure. But what does the system do? Well, the system tries to recreate that pressure by putting more molecules into the gas phase, right? So vaporization gets faster, or we get more vaporization. So as the pressure falls, the system tries to compensate by evaporating more to try to build the pressure back up. And of course, the opposite would occur if I reduce the volume. That would increase the vapor pressure. So what happens? The system tries to reduce it back down by having more condensation occur, taking gas out of the gas phase back into the liquid phase to try to get back to that starting pressure. Right? So this is, plays back into Boyle's law, right? Where, volume goes up, the pressure initially goes down. In this case, the system can respond and try to recreate that pressure, right, to keep the pressure constant. Right? Okay. it's a little bit about vapor pressure. Well, what are some of the things that will influence vapor pressure? Well, the big one here is temperature, right? So if you take a liquid, it'll have a certain vapor pressure at room temperature. If I increase the temperature, I can create a situation where I have higher vapor pressure, right? Because as I increase the temperature, I'm going to get more kinetic energy. I'm going to have more molecules that can evaporate. I'm going to get more molecules into the gas phase. I'm going to have a higher vapor pressure. Okay? So temperature increases, vapor pressure increases. Now, if we look at this graph, we can see that especially for certain molecules, very small changes in temperature can make very big changes in vapor pressure. So in other words, it's not a linear increase, right? We don't just double the temperature and the vapor pressure only doubles, right? You know, if you were to double the temperature, the vapor pressure is going to do a lot more than doubling typically. So you can see here how the vapor pressure changes from, say, room temperature in water, where you have very little vapor pressure, right? Just a few torr. At boiling point, right? The vapor pressure is way up here. At 1 atmosphere, right? And notice, right, this is a special point, right? The vapor pressure at 1 atmosphere. So whatever temperature the vapor pressure of your liquid equals 1 atmosphere, 760 millimeters of mercury or torr, that is what we call the boiling point. That is when a liquid will, quote, boil. And on the next slide, we'll talk about what we mean by boiling. So what is the boiling point when we refer to that? So, sometimes we think about boiling, vaporization sort of as the same thing, right? Well, they sort of are the same thing. Boiling point is just a specific point at which what we call boiling occurs. And boiling is a different sort of form of evaporation. So normal evaporation occurs only on the surface of the molecule, or only on the surface of the liquid. But when you reach the boiling point, we have the ability to vaporize anywhere in the liquid. So internal, non-surface molecules can now vaporize, can now go from the liquid into the gas. So again, this point is reached when the vapor pressure is the same as the external pressure. So if we think about atmospheric pressure as 760 millimeters of mercury, when the vapor pressure reaches 760 millimeters of mercury, whatever temperature that occurs at, that will be the boiling point. That'll be when this boiling can occur, or when you can have vaporization of any molecule in the substance, whether it's surface or internal. Now, the normal boiling point, right, just go fine, is the boiling point at 1 atmosphere, at normal atmospheric pressure, right? We call it the normal point. Now, if you change the pressure, of course, you still boil it, right? But if you change atmospheric pressure, you get a different boiling point. And so the boiling point of material or liquid will depend on the external pressure, right? Where it boils at 1 atmosphere is called normal boiling point, but when that material is at other external pressures, we see the boiling point change. So for a quick example here, we see water boiling at essentially the temperature when you're essentially at sea level, right? This is where normal is, right? 100 degrees. Elevation is about 1 atmosphere. If we go up and up and up, so we go into, up to say Denver, so a mile high in altitude, external pressure is now about 80% of normal. The boiling point drops about 6 degrees. If you go up even higher to say 20,000 feet, so into some of the high mountains, you get atmospheric pressure that's about half of what it is at sea level. And so the boiling point of water drops even more. down to about 80 degrees or 83 degrees. And so the idea here is that it doesn't have to work as hard to reach these lower external pressures. So to boil, right, we have to get the vapor pressure up to meet atmospheric pressure. So if atmospheric pressure is lower, we don't have to build up the vapor pressure some more. It's easier to do that, so we reach it at a lower temperature. Okay, so we're going to pause the video here. In the next video, we'll pick up talking a little bit about the energetics. So what are some of the math that we can do here?